Hello, so in this video we're going to look at finding the components of the Lorenz transform. In the last video we wrote the Lorenz transform in terms of hyperbolic functions of hyperbolic angles because we thought of the Lorenz transform to get a kind of more intuitive feeling for it in a very geometrical way. We considered it as a rotation of space-time axes to describe the hyperbolic nature of space-time. And how to go from one reference frame to another in special relativity. But that was a very geometric approach, hence why we used hyperbolic functions of hyperbolic angles. However, for practical purposes, it's a lot more useful to have the Lorenz transformation be written explicitly in terms of components, where those components are some kind of functions of velocity, such as the Lorenz vector. So we'll look at doing that in this video, and we'll also talk in detail about an application of time dilation, which is the decay of muons due to cosmic rays interacting with atoms in the upper atmosphere. And so this is all going to be about Lorenz vectors, time dilation, and we'll understand, therefore, some of the work of that man with that lovely white beard with those cool-looking bits of maths behind him, which unfortunately are blurred, but we'll go through some of the maths in a much more clear form in this video. So, from the last video, we've talked a fair bit in detail about time dilation, so I'm just going to go through this quickly, but relate it to a concept of proper time, which I'm not sure if I've mentioned before, this idea of proper time. Well, from before, we've seen very regularly now this expression, which relates to the space-time interval for the, if you like, moving observer, so in the prime reference frame, to the space-time interval concerning events associated with the moving observer, but from the perspective of the non-prime reference frame. And I won't say more about the purple equation because we have gone through it quite a lot in past videos. But it's worth kind of summarising what the terms are. So c is our speed of light, which both observers agree upon because we're assuming our moving observer is not accelerating. Dt prime is kind of the time interval between events which occur at a fixed distance. So if we're talking about two events, it's events which occur essentially at the same place according to the primed reference frame, so according to the moving observer or relative to the moving observer. And dt prime is the time interval between those events. dt is the time interval between those events for the stationary observer, or from the stationary observer's perspective, and dx is the distance between those events in the direction the moving observer is travelling. Because if the moving observer is travelling, then if the events don't seem to occur at any spatial distance relative to the moving observer, then the stationary observer will see one event being at a different location to another. And I've gone through that quickly because we talked about that in some detail before. But it's worth saying that dt prime is quite special. You might go, well, it's quite special because we can have expressions involving dt prime where there's no dx prime, so space-time intervals which depend solely on the time-like components of forward position. But more especially, the thing about dt prime is dt prime is how long things are taking from the moving observer's perspective, including how, essentially, if you like, giving a rate at which time is passing from the moving observer's perspective. And so when we're analysing anything, moving particles, particles that are decaying as they're moving, well, the particles will decay in accordance with how fast they perceive time is going. So if we have a particle that's kind of decaying, and let's say it takes 5 seconds to decay when it's at rest relative to us, well, when that particle starts moving really quickly relative to us, the particle still thinks it's going to take 5 seconds to decay, but because of this equation, this time dilation, it will seem to take a lot longer for us. But it will still, according to the particle, take 5 seconds just as it did before. And so dt prime is kind of a natural way, a natural passage of time for the moving observer, and therefore when we're talking about decays of particles and things like that, because these things happen in accordance with time from the particle's perspective, dt prime is if you like the correct measure of time, so it's sometimes called a proper time. You also see proper time in general relativity. However, I'll leave a discussion of proper time in general relativity for a general relativity playlist if ever I make one. We have plenty to explore here. And as I say, providing the particle that is moving less than the speed of light, which if it has positive rest mass it definitely has to, then dt prime, so time from the particle's perspective, will be less than dt, so time from our perspective. So it looks to us as if kind of time has slowed down for the particle. The particle seems to be taking a lot longer to do things it would do normally. Now, kind of an example of kind of a consequence of this kind of thing is, moving particles taking longer to decay than when they're at rest, and we'll go through detail of that in a moment, because I know I mentioned it a few times, but it's worth going into actually, the details of it. But also, as we'll see in the video after this, this kind of time dilation is also responsible for ultimately predicting, E equals mc squared, and therefore is fundamental in our understanding of nuclear fusion processes that power the sun, nuclear fission processes which kind of supply energy to the Earth, and also, unfortunately, nuclear kind of fission process involved in kind of modern weaponry as well. So the idea of time dilation has far-reaching effects beyond, beyond the kind of immediate consequences of things like particles taking a lot longer to decay from our perspective when they're moving very quickly relative to us. And so now we'll actually go on to try to both describe time dilation in a bit more detail and also derive the components of the Lorenz transform more fully to get an equation that describes time dilation more clearly than this, so it tells us how dt prime dt will vary just on kind of the velocity of the moving observer. And then we'll be using this to get one component of the Lorenz transform explicitly in terms of velocity, and then using hyperbolic identities we can get the other components. So when we're deriving the components of our Lorenz transform in terms of velocity, we have a couple of sanity checks. So we have a couple of kind of extreme cases for our function phi of v, where phi is our hyperbolic angle, describing the angle at which we're rotating our space-time axes to go from kind of the components of a full vector in one reference frame to the components in another reference frame. And these were our kind of like statements that we argued. So whatever expression we end up for our kind of Lorenz transform, the component should ensure that our essentially our hyperbolic angle phi as a function of velocity satisfies these conditions. So when v is 0, the hyperbolic angle should be 0. And when v approaches, well, as v approaches the speed of light, then the hyperbolic angle should approach infinity. And we also, in our previous video, wrote the Lorenz transform, so this lambda matrix, explicitly in terms of hyperbolic functions of the hyperbolic angle, and we had these kinds of expressions. So the top expression in the black box defines the Lorenz transform. The middle equation in the black box shows how this Lorenz transform has to relate the components of a 4-vector I call V in the non-prime reference frame to components in the prime reference frame, where the index 0 indicates we're talking about the time-like component, and the index I indicates we're talking about the space-like components of a 4-vector. And then the bottom equation shows the same thing as the middle equation, just in terms of more explicitly tensor notation. No, don't worry, you won't be needing much tensor notation. You can just think of it, think of the bottom equation as a more abstract version of the middle equation. Providing you understand the middle equation, that's all we will really need. And we have our graphs here showing how shine and cosh vary with the input. In this graph, the input is x, but for our purposes, we're using phi as our input. But just to show visually what cosh and shine look like, it's worth having a graph. And at the end of this video, we'll be tracking that the components of a Lorenz transform imply that phi, a hyperbolic angle, it can be written as a function of velocity, which satisfies the two limiting cases in the blue box. Because it's always worth, if you're trying to find a solution to something, to have sanity checks, so you can check at the end that what you've done seems legitimate. So now we're going to find the first component of our Lorenz transform matrix, which I gave the letter A on the, just a moment ago. So it's the component which is like, at the kind of top left-hand corner of our matrix. And we're going to find this component first because this component concerns time dilation, and we talked extensively about time dilation mathematically, so it's a good thing to start with that in terms of finding components of the Lorenz transform, and we'll then use hyperbolic identities to find the other components the moment we found this one, because it's worth saying that all of the components of a Lorenz transform are just kind of, dependent on cosh of phi or shine of phi. But cosh of phi and shine of phi are related to each other, and if you know one, you know the other. So the moment we found even just one of the components of the Lorenz transform, we can find all the components, which is the beauty of really it. And it's because, rotational matrices have that kind of nice symmetry to them. Generally, unless I suppose you're working in a really bizarre space, a rotational matrix is going to have some kind of symmetry in terms of its components. For example, say we couldn't work out what the rotation matrix was for a vector living in Euclidean space. Well, if we knew one component, we could probably work out the others just as easily. So anyway, we're going to find one component to start with of a Lorenz transform, and that's going to relate to time dilation effects. So, our kind of like setup is if we write, you know, instead of dt prime, if we write d tau, so tau is just another symbol in this case for t prime. I'm using tau because now I want to make more and more uses of the term proper time, because, you know, it doesn't matter too much for this video, but in future videos I will start to just talk about proper time. And so it's good to get used to it kind of here in this one. So the time dilation equation we had before, relating the space-time interval in the primed and non-primed frame, can be rewritten in the kind of top, in the form of the top equation. And also we can make the top equation a little more pretty, if you like, by defining something called beta. Now, beta is traditionally used to represent the fraction of the moving observer's velocity from the perspective of the stationary observer, and then the speed of light. And this fraction is important because it's actually this fraction that determines how significant time dilation and other relativistic effects are. It's always the ratio of velocity to the speed of light that counts. So if we just substitute in our kind of expression for beta, we can say, well, the time interval, the proper time, is just the square root of 1 minus speed squared, and then outside the square root we have dt. And a good way to check whether this is at least possible, kind of logically, or at least mathematically, is to check that the units, both sides of the equation, match. Well, the units of proper time and of time from the stationary observer's perspective is both seconds, and then beta has no units, and consequently the units of both sides of the equation match. So we're on good grounds. And it's also worth saying, I just say to make this extremely clear, but also because this is going to become a very important fact when we derive our kind of first component of the Lorenz transform, the top left-hand component, or the lambda naught prime component if we're using kind of an index notation. But the very important fact is that this expression we have for time dilation only works if we're assuming dx prime equals 0. So if we're assuming from the moving observer's perspective, the events occur at the same place relative to them in space anyway. If that isn't true, then we would have a more complicated expression relating d tau and dt. Now, if we write everything we've essentially said, so our equation for d tau, the fact that dx prime is 0, the fact that the primed and non-primed components of the 4 vector, in this case 4 position, are related by our Lorenz transform, then putting it all together we can say confidently this bottom expression. And if you're unsure, I would take a moment to pause and just verify with yourself that this is true. Essentially, we're just relating the components of 4 position in the primed and non-primed frame using the Lorenz transform, but in the special case where dx prime is 0, so there's no spatial distance between the events from the perspective of the moving observer. Now, once we have this, we can look at it and, using kind of rules of matrix multiplication, break this down into 2 simultaneous equations. So the first bit we get by looking at this kind of expression involving our 4 vectors and the Lorenz transform And if we kind of try to get d tau in terms of, well, if we try to get d tau in terms of the components of forward position from the stationary observer's perspective, we end up with this expression. So that's just kind of pure maths, if you like. There isn't much physics there. And we can do a similar thing to get the bottom equation, the spatial component of our forward position, but relating that value in the prime reference frame to the components of the forward vector in non-prime reference frame. So those are our two simultaneous equations, and as you might remember from school, the way you solve simultaneous equations is to rearrange and substitute one thing into another. These two equations might look more complicated than typical, simultaneous equations, but the logic works exactly the same way. Now we want an expression that is going to relate, ideally for time dilation, d tau and dt. So really, well, we in a sense, we already have an expression in the blue box relating d tau and dt. But if we can also get an expression between d tau and dt, but in terms of our hyperbolic functions, that is in terms of our kind of like components of the Lorenz transform, then we can compare the two equations and therefore work out one of the components of our Lorenz transform. And therefore, even though we've got one equation relating d tau and dt in the blue box, we want in this black box to also have an equation relating d tau and dt, so we don't want a dx appearing. So what we do is we rearrange one of the equations for dx and then substitute whatever we get for dx into the top equation in the black box. And when you do that, you end up with this expression. We're saying sine squared of phi is not sine of phi. It's just sine of phi all squared. Similar to kind of like when you have sine squared theta. But thinking of the Euclidean version. So now we have an equation relating d tau and dt. We realise that this equation at the moment seems to have both cosine and sine functions in it, which isn't really very ideal at all. We would just like either sine or cosine. Well, we can't do anything to really, well, it would be very complicated and lead to a very strange expression if we could change the cosine terms into sine terms. However, using the hyperbolic identity, we can clearly exchange sine squared terms for cosine squared terms, and thus end up with ultimately an expression between d tau and dt in terms of cosine or cosine squared. And when you go through this, and it's worth saying that this kind of bottom equation relating cosine and sine is valid for all inputs phi, because it's true just in how we define the functions cosine and sine. So there's not much physics there, but if we make use of this identity, then we can essentially have an equation relating d tau and dt in terms of cosine, and we've got an equation relating d tau and dt in terms of beta squared, and therefore we can, comparing those two equations, deduce an expression for cosine in terms of beta. Now, it's worth saying that I'm going to kind of like now kind of describe how we find the other components of the Lorenz transform, and then we'll talk about kind of an application of time dilation in terms of muon decay. but we will be using this component not only to get the other components, but also as a sanity check that phi of v behaves in a way that satisfies the limits we had before about what phi of 0 is and phi of c is. So before we found the first component of our Lorenz transform, but as we showed on the previous bit of the video, cosine and sine are related via a identity that works for all inputs phi, and therefore if we know one of the components of the Lorenz transform, we can find the other components, and that's what we're going to do now. So here's our Lorenz transform in all its glory. And we've already found one of the components. But as I say, we can now find the other components. And now because you know, if we're looking at cosine of phi v in terms of a function of beta, if you like, which is the ratio of v over c, well, this expression is quite bulky. It's a good expression because this expression, since c is just a universal constant, this expression is a function solely of, if you like, really just velocity. The only variable going into it is velocity. And therefore, we've found one of the components of our Lorenz transform. We found an expression just in terms of velocity, which is what we really want, because whilst hyperbolic functions give a geometric intuition to the Lorenz transform, it's not clear what cosh of phi of v would be from the moving, if a moving observer is looking at if a stationary observer is looking at a moving observer go by. What is much more clear to the stationary observer is how quickly the moving observer seems to be moving. So this expression for a component of the Lorenz transform in terms of, as a variable, at least just velocity, is much more ideal. However, it is quite bulky. It's a lot more bulky than our kind of cosine of phi of v. And so whenever there's a really bulky expression, but one that we can immediately see from our Lorenz transform will appear again, because, the top left-hand component and the bottom right-hand component of our Lorenz transform are the same, so it's at least going to appear once more, turn out to appear more than that. Whenever that happens, and given that the Lorenz transform is very special and something that occurs again and again in physics, it's really worth actually having a whole kind of factor that we just define to always equal 1 over the square root of 1 minus beta squared. And this factor is called the Lorenz factor and has the symbol gamma. Now, whether that's ideal, I don't know, because unfortunately, gamma is also traditionally the particle symbol for a photon, kind of a particle associated with electromagnetic radiation. And photons are therefore can be thought of as kind of being manifestations of the electric and magnetic fields which kind of compose light. And special relativity is all about light, so having gamma refer possibly to the Lorenz factor and possibly to light, I think is a little confusing, but we're stuck with this. So I will make as clear as I can in these videos whether gamma is referring to the Lorenz factor or to light. But at least for this video, whenever you see gamma, think Lorenz factor. And we'll see later on in the video that kind of gamma increases very, very, very rapidly as v approaches the speed of light, or in other words, as beta approaches 1. And you can kind of see that if you look at the expression for gamma, but it's this incredibly rapid increase in gamma which makes kind of, even tiny differences in velocity, if that velocity is very close to the speed of light, very significant. and therefore we can get a lot of information about velocity to a very high number of decimal places if something's moving incredibly quickly, and we have some way of gauging how long time has passed for it and how long time has passed for us, the stationary observer. But using the hyperbolic identity we looked at before between sine squared and cosine squared, we can say, well, this is going to be true, this bottom equation is true for all inputs phi. And, well, we've got an expression for cosine squared in terms of gamma. And therefore, using this identity, but replacing cosine squared with just a Lorenz factor gamma, which is true by definition because of how we've defined gamma, the Lorenz factor, we end up with sine squared phi is equal to gamma squared minus 1. But if you look at the definition of gamma and actually work through algebraically what gamma squared minus 1 will be, you'll end up concluding that sine of phi would have to be beta times gamma. Now that jumping to that last step is just a bit of algebra, which I leave to you as a bit of fun, because there isn't really any physics by that point to go over. And I want to leave you the opportunity to work out a bit of maths as we're going through this material, to hopefully make this material as engaging as I can make it. And it's worth working out some stuff, and also doing algebra and rearranging with things like the Lorenz transform, which are pretty cool, and far less trivial, I think, than a lot of the rearranging exercises that goes on in high school. Understandable reasons for that, because the Lorenz transform is an extremely abstract concept. But still, I think it's fun to practice algebra with something of deep physical significance. So you can really see the worthwhileness of kind of algebra. But that kind of note aside, now we have sine, we have cosine, and we have the Lorenz transform, which in the last video we justified was kind of these particular combinations of cosine and sine functions. We can rewrite the Lorenz factor now explicitly in terms of functions that depend on velocity alone. The only thing that can change for the gamma function or the beta function is the velocity v, because the speed of light is a universal constant. So although the speed of light is present in the Lorenz factor and in beta, it's not a variable, it can't change. So in short, we now have all of the components of the Lorenz factor being a function of velocity. And this allows us to directly calculate things like time dilation, annual length contraction, and so many of the effects of relativity much easier in a computational way than we could if we were stuck with hyperbolic rotations. Hyperbolic rotations are great for getting a grip of the Lorenz transform, particularly how the components relate to each other. It provides a much more geometric intuition than if we were going to try to jump to a description of the Lorenz transform in terms of velocity to begin with. However, in terms of computation, it is far easier to work with a Lorenz transform where the components are functions of velocity, rather than hyperbolic functions of rapidity factors, or in other words, hyperbolic angles. So now we've got this matrix, we can potentially calculate so much with it. Now this has been a fair bit of maths, and I promised I would go on to talk in detail about time dilation with muons, so that's what I'm going to do next. So now we talked a fair bit about finding the components of the Lorenz transform, and we've really designed that around the idea of time dilation. I thought it was about high time in this channel that I discussed an application of time dilation in some detail. Now in the next video we'll be looking at using it to prove E equals mc squared, the founding principle behind how the sun produces energy, and also ways to reduce energy in through nuclear fusion and uranium rods, and also unfortunately a fact that has been militarised in the past as well. But as a more direct application of time dilation, we can talk about something called muons and consider how long they take to decay and the relevance of that in kind of understanding astrophysical processes. So firstly, what is a muon? Well, in the kind of standard model of particle physics, there's two types of matter particles. So there's quarks, and quarks make up particles like neutrons and protons. But as well as quarks, there's also leptons, so like the electron, and the electron neutrino, and those are kind of two stable leptons, but there are other heavier kind of versions of those two things. And one kind of heavier version is the muon and the muon neutrino. So a muon is like a heavy electron, but because the muon is like a heavy electron, it can spontaneously decay into, an electron. Other particles reproduce as well, but with very little mass. So the main thing is, because it has a lot more mass than the electron, it can, decay into an electron, and those other particles with tiny mass. And because if you wait long enough, anything that can spontaneously happen will, at some point, inevitably muons will decay, and the details of this process is given in quantum field theory. If you look at kind of quantum field theory, you'll kind of study how kind of decay processes can be thought of as essentially interacting quantum fields, but we don't need it for this purpose in this video. We're just kind of interested in thinking of particles as almost classical particles. So here we've got a muon, and the muon is decaying into an electron, an anti-electron neutrino, and a muon neutrino. Now, the reason we need these neutrinos is to conserve something called electron number. It's a quantum number that is conserved thanks to quantum field theory. For our purposes, the neutrinos don't really matter. The important thing is there can be spontaneously this kind of decay, meaning muons don't live naturally for very long. And you might ask, well, if muons don't live for very long and decay, then how are they created in the first place, and why are so many of them created that they're kind of of much relevance discussing? Well, muons are created in something called a cosmic shower. So a cosmic shower isn't where a star kind of puts a large shower head over the Earth. A cosmic shower is the result of a cosmic ray interacting with atoms of gas in the upper atmosphere. So a cosmic ray is kind of a stream of high energy particles from possibly the sun, but it could also be from other astrophysical processes in the cosmos, hence the term cosmic ray. Now these cosmic rays are hitting the atmosphere all the time. They're not particularly damaging. There are certain things that would be damaging to Earth, but we're very unlikely to encounter them, at least in the near future, if ever. on the Earth anyway. So, primary cosmic ray has tons of high energy particles. These particles collide with atoms in the upper atmosphere. Then these atoms, having now tons of energy, start to decay. There might be particle interactions between kind of the electrons in the atoms and the particles in the cosmic ray, or maybe the protons and neutrons in the nucleus of the atoms in the cosmic ray, and then products are formed, but those products tend to be unstable and they decay, or sometimes something will be knocked off an atom by particles in the cosmic ray, and then that thing will then collide with other atoms, and so you have this whole kind of sequence of events, a very dramatic time caused by this single primary cosmic ray. Now, cosmic rays end up directly producing a lot of kind of kaons and pions, and these are kind of particles made up of quarks. At least for pions, the reason you might think that we get a lot of pions from a cosmic ray interacting with kind of a nucleus of an atom in the upper atmosphere is because pions are in a sense already present within the nucleus. They're exchanging this, kind of transmitting a strong nuclear force between particles in the nucleus, so between protons and neutrons. So in a sense, pions are already present and they're just kind of ejected out when the nucleus is given enough energy. I mean, this is a very classical analogy and it's not entirely accurate because it is an analogy, but it gets kind of the main points across. But pions and kaons are themselves unstable, and they naturally decay, and products of that decay is often muons. So we get a lot of muons through the decay of pions and kaons, and pions and kaons are produced kind of by kind of interaction between particles in the cosmic ray and atoms in the upper atmosphere. But as I said, these pions don't live for very long. I said the pions don't, but for our purposes, the main thing is the muons don't live for very long. They'll decay into electrons, and we can see how fast they decay. And when at rest, relative to us, we will observe the muon taking 2.2 microseconds to decay. However, if they always took, on average 2.2 microseconds to decay, and they were produced in the upper atmosphere, then, even if their speed was very relativistic, so a significant fraction of the speed of light, they still wouldn't travel enough distance by the time they've decayed to reach the Earth's surface. However, we observe a lot of muons on the Earth's surface, and the reason is because of time dilation. Now, when you're calculating how significant time dilation will have to be, you need to know something about the velocity of the muons. But the difficult thing is that cosmic rays, the particles in cosmic rays can have a large variation in energies, because cosmic rays are produced by so many different processes in the cosmos. There isn't like a standard energy of particles within a typical cosmic ray, because there's no real typical cosmic ray. And therefore you have a large range of energy of particles in the cosmic ray, which leads to a large range in energies of the muons which are produced in the end, in this cosmic shower of particles. But, almost always the energy of the, I say almost always, for us to detect them due to time dilation, we would require that the muons have kinetic energy similar, if not significantly greater than their mass. And we'll look at the formula for kinetic energy in the next video. But the key thing is, there are muons, plenty of muons in fact, that are moving relativistically, and they have to be moving relativistically, because the only way we can detect them is if, from our perspective, they're taking a lot longer than 2.2 microseconds to decay. So if we take, for example, a value of beta of 0.98, and there are some values of beta which are larger than this for muons that reach kind of as detectors. But if we take beta equals 0.98, then we get a Lorenz factor of 5, so the muon would take, from our perspective, not 2.2 microseconds to decay, but 5 times 2.2 microseconds, or in other words, 11 microseconds to decay. And if you multiply that time by the speed, so 0.98 times the speed of light, you'll find that the distance these muons will travel, or will be able to travel, actually covers the distance between the upper atmosphere and Earth's surface, so we can detect them. So really, kind of like our detection of muons on the Earth's surface, given that they're produced in the upper atmosphere and decay, is reliant on the effects of time dilation. Now, time dilation here is quite important because muons, as I say, are resulting from initial interactions between atoms in the upper atmosphere and cosmic rays, so we can learn something about cosmic rays and therefore about some very unique processes in the universe through these muons and their energies. And so, understanding being able to detect the muons is very helpful to us, and it means, and thanks to time dilation, we can detect the muons on the Earth's surface with detectors on the Earth's surface, and we don't have to put detectors in the upper atmosphere or even in space. So from a financial perspective, that's incredibly handy, because it's a lot cheaper to have detectors working on the Earth's surface than to have them, being built on the Earth's surface, but then transported to upper space and be operated, kind of in space. Now you might think 2.2 microseconds, the lifetime of a muon at rest relative to us, is quite short, but it's worth saying that the decay of muons happens thanks to the weak interaction. And the weak interaction is called weak because it's extremely ineffective compared to the strong interaction. And 2.2 microseconds therefore is typical of weak interactions because it's actually quite a large lifetime. If you look at particles that decay via strong interactions, you're traditionally looking at lifetimes within the order of nanoseconds or maybe even picoseconds. So 2.2 microseconds is actually quite large in the particle realm. However, 2.2 microseconds isn't long enough for muons to reach the surface, given that there's this kind of limiting speed of the speed of light. So I hope it was helpful to have a bit of an in-depth dive into an application of time dilation, and now we're going to move on to looking at the Lorenz factor in some more detail, more visually. So here I've got kind of a couple of curves. I've got the Lorenz factor being my blue curve, and I've also plotted essentially beta squared as my orange curve. The function for my orange curve. Both of the inputs into these functions are the value of beta, so beta can range from 0 to 1. But what we can see is that even though, beta squared by definition is going to be quadratic, it's a quadratic function of beta. Essentially, this, orange curve is the curve y equals x squared, if you like. Because the y-axis is, beta squared, and the x-axis has an input beta. And quadratic curves, like if you think of the curve y equals x squared, tend to look like they increase quite rapidly as x grows quite big. Now, it's worth saying x here is, or for our purposes, beta is varying between 0 and 1, so maybe the rapid increase wouldn't be as significant, possibly. However, quadratic curves still rise quite steeply, but that rise is nothing compared to how rapidly gamma rises as kind of beta, approaches 1 or as v goes to c. And in fact, if you put, beta equals 1, or in other words, v equals c, into a calculator or a computer, your Lorenz factor, the gamma factor, will blow up. And so time dilation becomes very significant as v goes to c. The effect tends to be quite small, even if v is just a tenth of the speed of light. So in other words, if beta is about 0.1, as you can verify for yourself. Really for, although, now modern experiment can, still detect relativistic effects when beta is 0.1, you only really start getting what in everyday life we would ourselves be able to, directly infer from just our eyes as being, very, very significant relativistic effects, and, our stopwatches and stuff. When beta, lies around, 0.7 to 0.8, or beyond. But, as beta goes to 1, gamma goes to infinity. So, then, if beta is very, very close to 1, then tiny differences in beta will result in drastic differences in gamma. But anyway, this has just been a kind of, not the most exciting graph, admittedly, but it's worth having a look to see quite how rapidly this kind of Lorenz factor, and therefore things like time dilation, kicks in as beta goes to 1 or v goes to c. So we're now going to do, if you like, sanity check, although that's quite a strange term considering we're dealing with relativity, but we at least use logic, at least for one of the limits, kind of common sense, daily common sense, to derive limiting values for how our hyperbolic angle, else known as the rapidity factor, in the context of special relativity anyway, can depend upon velocity. And these were kind of limits we derived even before we had an expression like the one we have here for for a hyperbolic function of this rapidity factor. So in other words, one of the components of the Lorenz transform. Well, now we've got this component for the Lorenz transform, and we've got, as we always had, a graph for sine and cosine, because this graph existed even before, relativity. We can now check that, our expression that defines cosine phi, and therefore also, will indirectly define sine phi through the hyperbolic identity, satisfies the limiting cases we saw before. So these were limiting cases for phi, our rapidity factor. And if we're going to put in to check that these limiting cases work, the relevant values for B into our expression involving beta, then we find that indeed the limiting values and the function we derived for cosine of phi of V are consistent with each other. So for example, if we pick V is 0, or in other words beta is 0, then cos phi of 0, using our function we derived in this video, is going to have to equal 1 divided by the square root of 1 minus 0 squared, so it's going to have to equal 1. And if we look then at when cos of phi, if we look at what inputs phi, would cos of phi be 1? Well, cos is our green line, and so, cos of phi is this kind of like green curve. And so if we look at where cos of phi is 1, well, cos of phi is 1 where the input, so when phi is 0. Therefore, phi of 0 equals 0 is entirely consistent with defining cos of phi of V to equal 1 divided by the square root of 1 minus beta squared. And you can do a similar thing with the other condition, just using the fact that, as this graph implies, cosine diverges to infinity as the input, so as phi goes to infinity. And therefore now we've shown that kind of, when we derive the components of the Lorenz transform, and particularly its first component, we have defined hyperbolic functions of the rapidity factor in such a way that kind of the rapidity factor, or the hyperbolic angle, obeys the limiting values we justified it would have to obey for a physically sensible kind of hyperbolic angle relating to special relativity in the last video. Now, so far in our playlist, after we looked at strings and Maxwell's equations, we've talked a lot about the theory and got quite abstract. In this video we talked a little bit about time dilation, but the future videos now we've got both a solid understanding of calculating variant quantities from finding lengths of 4 vectors, and also for relating components of 4 vectors in different reference frames using a Lorenz transform, which we've now got an expression for in terms of just velocity. We've done so much of the back work, and we can move on to lots of applications. So in the next video we'll be looking at deriving equals squared, the key behind fusion processes, and the energy generation in the sun. And we might also include a bit of astrophysics history of alternate hypotheses and go through that in more depth. Because I mentioned the other ideas briefly in the introductory video where I went through the history of relativity. So that might be a worthwhile thing to do. And then in future videos we'll look at things like tachyons, we'll look at neutrino oscillation in more detail, and I'll also try to relate relativity we covered in this playlist, the special relativity, a bit to general relativity, such as linking the time dilation we talked about here to gravitational time dilation associated with things like black holes. So that's where we're going in this playlist. I hope some things there sound exciting, and I think I might be able to keep this video under an hour, so I'll finish here. But I hope you've enjoyed this, and hopefully see you for more soon.